Today we'll cover level acceleration data reduction. Data for this lab includes time from your watch, airspeed and altitude from the gauges at your section, outside air temperature from above the pilot's head, manifold pressure and RPM off the engine gauges, and fuel quantity off of this gauge, as well as your flap configuration. Step 1 is to apply instrument corrections to the recorded airspeeds and pressure altitudes. Again, you recorded airspeed through the acceleration, so there's lots of airspeeds and really only one altitude, but you're going to take that data and apply the associated instrument correction and position correction for airspeed, and in the case of pressure altitude, just the instrument correction for pressure altitude. These steps should be familiar now that you've done this a few times on the various labs. Step 2 is to convert calibrated airspeed to feet per second and then plot versus time. So here's calibrated airspeed in miles per hour, just convert that to feet per second and then generate that versus time. With that plot, we're going to add a third order curve fit in Microsoft Excel and make sure you display the equation, because in step 4 we're going to take the derivative of that equation. That gives us acceleration, or dv/dt, taking that derivative. And with that equation, we now can substitute in all the times we took data at, so basically 0 through 90 seconds in 5-second increments, into this equation and calculate the associated dv/dt at each time step. Next, we'll calculate density ratio using the equation we've used in the past lab. So we'll just take our instrument corrected pressure altitude, in this case 7405, put in our ambient temperature 6 degrees, and again these did not change throughout the acceleration, so this sigma works for all time steps. Step 7 is to calculate true airspeed using the equation that involves calibrated airspeed and the square root of sigma. So we'll take all these calibrated airspeeds in feet per second and then divide by the square root of this sigma to give us our true airspeed at each time step. Next, we'll calculate our test weight. So you don't burn a lot of gas in the level acceleration. In this case, we started with 54.6 gallons, and by the end it was 54 gallons, so we burned 0.6 gallons, which means our midpoint is 54.3. So we'll substitute that in to calculate our test weight. For this problem, it was 3,367.8 pounds. Step 9, we'll calculate our thrust horsepower in excess using this equation. We have our test weight, G, 32.2, dv/dt data, our true airspeed, and the rest just puts this in horsepower. So that's the columns of data that you're going to use along with this value for G and calculate thrust horsepower in excess. Once we have this data, we're going to correct it for non-standard weight. So we just calculated this, divide by the weight ratio to the 3/2 power. Our standard weight for the Cherokee 6 is 3,400 pounds. So now we have this column of data. Next, we'll calculate rate of climb in feet per minute, starting with our weight corrected thrust horsepower in excess, divide by our standard weight of 3,400 pounds. These are more unit conversions, and that gives us our rate of climb in feet per minute as a function of time. Repeat all calculations for the other 3 level accelerations. So steps 1 through 11, you're going to repeat for the second level acceleration, the third, and fourth data. Once you have all 4 level accelerations calculated in one big spreadsheet, like shown here, you'll then be able to generate plots. The first plot to generate is rate of climb versus calibrated airspeed. And in this case, you're going to want to group the data in flaps up versus flaps 10. So take the flaps up higher altitude, the flaps up lower altitude, and generate one plot. Once you have rate of climb versus calibrated airspeed, you're going to smooth a curve through that data. Likewise with the lower altitude data. Once you have a curve, you can then figure out what's your best rate of climb, or your Vy, which is basically the highest point on the curve. You'll have one of those for each altitude. Next, you can obtain your best angle of climb by drawing a line from the origin tangent to the curve, and where those intersect, you'll get Vx, or the best angle of climb. So you'll have one plot for flaps up and then a second plot for flaps 10 degrees. Once you have this data, especially these 2 points on this green one, the 2 points on the black one, you can generate an altitude versus Vy and Vx. And so these 4 points then can be plotted, right? Each point has an associated altitude. In this case, these 2 points were at 7,405 feet. These 2 points were at 3,370 feet. And so that generates these two graphs. And just draw a straight line connecting them. And where these two meet is your ceiling. It's the highest altitude in theory that the airplane can climb. The other thing you'll see here is the published Vy speed for the Cherokee 6 is 105 miles per hour. And so our data comes fairly close to that. In this case, it looks more like 103 or so. So pretty close to the published Vy speed. And this is for flaps up. The data for flaps 10 degrees is not quite as well behaved because our data doesn't really follow the normal curve that you would expect. So this data is probably not the best data. The flaps up data looks pretty good, but the flaps 10 is a little bit suspicious. In the end, we can still plot these things and try to estimate that our ceiling in this case would have estimated around 14,000 feet. And finally, we can plot our thrust horsepower and excess weight corrected versus calibrated airspeed, similar to the rate of climb plots, but in this case, the y-axis is thrust horsepower and excess and weight corrected. So looks similar. You again want to plot flaps up data, both sets of flaps up data at the altitudes, and then fair smooth curves through those data, and then generate a similar plot for flaps 10.